In section 7.1, we talked about what a function was, and in this section, section 7.2, we are talking about how we can represent a function. And there are 4 different ways we can do that. They are in our learning target. So the first is as a set of ordered pairs. The second is as a table. The third is as a graph. And the fourth is as a rule. So we're going to write those 4 ways right over here. Again, the first is as a set of ordered pairs. So I put an example of a set of ordered pairs there. 2, 4, 3, 6, and 4, 8 is a set of ordered pairs. The second is as a table. So a table would look like this, where we have the X column and the Y column. We could set up our tables as vertical, or we could have a table more long than it is wide, and then that would be the same thing. The third way is as a graph. So I have an example right here of a graph. And the fourth way is as a rule. And another word for rule is equation. So I have here an example of a rule would be y equals 3x plus 2. So there are 4 different ways to represent functions, and we also have mappings that we discussed earlier, or we could put it all into words. So we're going to take a look at example 1 that's given in words, and we are going to make a set of ordered pairs, a table, a graph, and a rule for that example. So in this step, the first thing I'm going to do is come up with a set of ordered pairs that would fit the situation. It says, while walking, I burn about 257 calories per hour. The total number of calories burned is a function of the number of hours I walked. So we're going to represent this with a set of ordered pairs, a table, a graph, and in words with a rule. The way I came up with the set of ordered pairs is I knew that X was the number of hours I walked. So if I know that I don't walk any hours, I won't have burned any calories. So 0, 0 is a point. If I walk 1 hour, it says up here, I burn 257 calories per hour. So if I just walk 1, I burn 257. If I walk 2 hours, I burn 514. And if I walk 3 hours, I will burn 771. Now there's no reason I stopped there. I could keep going. Now we're going to fill out a table with the same information. So again, I said that the X value was the number of hours, and the Y value is the number of calories burned. So in the table, I have filled out my X column, which is hours, and it's important to put both the X and the word hours. And I filled out the Y column with calories burned, and I matched my hours and calories burned with the same numbers that I used in my ordered pair. Now it's time for number 3, which is to graph this, and so my X value down here are going to be hours, and my Y value are going to be calories burned. So it's important to put labels with your axes, and we are going to just make this easy and have our Y values go up in increments of 257. That just makes it easy. And the Y values are going to go up by 1, but I'm going to give it a little bit of space. So you'll want to pause the video to catch up to where I am. So hours is labeled on the x-axis, and calories burned is labeled on the y-axis. And I've just chosen to do every 3 to spread them out a little bit. So every 3 ticks is 257 calories on the y-axis, and every 3 ticks is 1 hour on the x-axis. So now I'm ready to go ahead and plot the points. So I'm going to plot 0, 0, 1, 257, 2, 514, 3,771. And then I ask myself, is this a continuous graph? So does it make sense to connect the dots? And it certainly does, because I will burn calories if I just walk for a half an hour. So I'm going to go ahead and connect the dots. And I put an arrow on my line to show that it continuously goes up there. And I don't have an arrow down on this side because it would not make sense to walk a negative number of hours. So now I'm going to go over to example 4, or part 4 of this example, and we are going to let x equal the number of hours. That's what I have here, so I'm going to write that here. And let y equal the calories burned, so I'm going to put that here. And remember that this step is called defining the variables. So I've defined my variables. X is the number of hours walked, and y is the number of calories burned. And in words, we would figure out the number of calories that are burned by multiplying the calories burned per hour times the number of hours. So in words, the number of calories burned equals the calories burned per hour times hours. Now we're ready to write the rule in a mathematical equation. So you can see the number of calories, which was y, is down here. Y equals the calories burned per hour, which we knew was 257, times the number of hours, which we said was x. So y equals 257x is the equation or rule for this function. In example 3, we are given a graph and we are asked to circle the table that represents the same information as the graph. So up here it says when you're given one of the 4 ways to represent a function, you can usually find the other 3 ways to write it. So what we're going to do is we're going to find some points that are on this line and choose the table that has those same points in it. So I notice that it goes through the origin 0, 0, and you notice that 0, 0 is in all 3 tables, so that one doesn't help us. I see this point down here is the point 1, negative 3. So what I'm going to do is I'm going to look for my tables to see if it has 1, negative 3 in it. And you can see that 1, 3 is in this one, so that doesn't work. 1, negative 3 is here. And 1 is not even in here, so it doesn't help us much. So it's still between B and C. So let's go back to this point. That point is negative 1, 3. So with negative 1, 3, I'm going to look in my table to see if negative 1, 3 is there. So in this table here, negative 1, 1 is in there, so that's wrong. So that means the correct one is the one that has 1, negative 3, so that is B. So the correct answer is B. In example 3, which equation could be a view of the function represented by the table? So this time we're looking at a table, and we're trying to match which one of these matches the table. So if I choose the point 2, 0, so when x is 2, I should get y equaling 0. So if I plug 2 in for x, do I get 0 out for y? This one is no. If I plug 2 in for x, I get negative 4 for y. So number 1 is out. If I plug 2 in for x here, 2 minus 2 is 0, so that one might be right. If I plug 2 in for here, I get negative 2 plus 2, and that's 0. So either one of these two could be right. So let's go ahead and choose another point. Let's choose the point 0, negative 2. So if I plug 0 in for x, I get 0 minus 2, which is negative 2, so it works there. If I plug 0 in for x here, negative 0 is just 0. plus 2 is 2, so I should get 0, 2 for this one, but I don't have it here. So that means the correct answer is Roman numeral 2. Oops, I kind of crossed it out, but that's the right answer there. All right, let's move on to example 4. In example 4, you can make 3 gallons of liquid fertilizer by mixing 10 teaspoons of powdered fertilizer with water. Represent the situation in a table, as a graph, and as a rule. The first thing we have to do in this problem is figure out which of the variables is the dependent one and which one is independent. That's very important. So my question to you is, does the number of gallons of fertilizer depend on how much powder we have, or does the amount of powder depend on how much liquid we have? So the correct response is that the gallons of liquid fertilizer depend on how much powder we have. So that means that the liquid is the dependent variable, which is your y, and the teaspoons of powder are the x values because that's independent. The next thing we have to do is figure out how much liquid we get depending on how much powder we have. So if we have 0 teaspoons of powder, obviously we would get 0 gallons of liquid. And up in the top it says if we have 10 teaspoons of powder, we would get 3 gallons of liquid. So 10, 3 would be a point. And then if I had 20 teaspoons, that would mean I could make 6 gallons. 30 teaspoons means I would make 9 gallons. So I'm going to fill out my table according to what we just talked about. Making that table helps me with my graph, so I know that along my x-axis I'm going to have teaspoons of powder here, and along my y-axis I'm going to have gallons of liquid, and then I can plot these points. So I'm going to choose a scale that makes it easy to plot those points. So you'll definitely want to pause this so that you have enough time to graph that. Notice that I did connect it because if I have 5 teaspoons of powder, I could still make some liquid fertilizer with that. So I want to connect the dots. I would not go into the negatives because it wouldn't make sense to have a negative number of teaspoons of powder. We are going to now move on to writing this as a rule, and there's a little typo here. We need to change that to 3 because there weren't 4 parts to us doing this problem. So x we've already designated up here as the number of teaspoons of powder, and y is the gallons of liquid. So notice that we are not asked to write it as just in words like we were the last one. We just have to write the rule, but it's a little trickier, but not too much. We should recognize that since this goes through the origin and it's a straight line, it means it's a proportional relationship. And if you recall, proportional relationships have the equation y equals mx. So really, we only have to find m, which is the slope, and you can see the slope. It's rising 3 and running 10. Notice it's not a 2, it's a 10. We go up 3 and we go right 10 units, even though it's just 2 spaces. My slope is 3 over 2, over 10. Up 3 over 10 again. So my slope is 3 over 10, which makes my rule y equals 3 over 10 x. And again, I'm going to repeat, I knew that this was a proportional relationship because it went through the origin and it was a straight line. So we knew that the equation should have been in the form y equals mx. And so I just had to find my slope, and that was 3/10. This last problem in this section could be a lot more difficult if you did not read the directions. So make sure you're reading the directions very well. While exploring a planet, a robot descends at a rate of 272 feet every 2.8 hours from a hill peak 1,710 feet above sea level. This is the important thing that you read. We are going to round to the nearest 10 feet and to the nearest whole hour. So to the nearest 10, the 7 is in the 10 spot. So if I round that, that's 270. So we're going to round that to 270 feet. And then we're supposed to round to the nearest hour, whole hour. So 2.8 hours is closest to 3 hours. So it's 270 feet every 3 hours. So we're going to make a table, and keep in mind that we start the robot at the top of the hill, 1,710 feet above sea level. And right here it says descends. For those of you who don't know that word, it means it goes down. So we're starting at 1,710 feet. So after 0 hours, we are still at 1,710 feet. That's important. Don't forget to plug in 0 for your x to see what the value is. So that's the beginning of our table. Now, we know that after 3 hours, it goes down about 270 feet. So if I want to, I can use that, or I can figure out how much it goes down every hour. So it's my choice. I'm going to go ahead and say that that's going down 90 feet every hour, because if it's 270 feet every 3 hours, that would be 90 feet every hour. Since it's pretty high up, I'm going to use hours, and I'm going to go ahead and say 3 hours. So the elevation would have gone down 270 feet, which means the result is 1,440. So I'm going to plug that into my table. And then after 6 hours, it would go down another 270 feet. So that would be an elevation of 1,170. And after 9 hours, it would go down another 270, and that would be 930. So I'm going to plug those values into my table now. So to figure out the equation, what I'm doing is I am taking this 1710, that was the starting height, and I'm taking away 270 every 3 hours, which ends up being 90 every hour, and that's our unit rate, which we already know unit rate is the slope. So we're going down 90 feet every hour, and we start at 1710. So there are a couple ways I could write the equation. 1,710 minus 90 each hour, so minus 90x, is one way. So I have y equals 1,710 minus 90x. The other way I could write that is in slope-intercept form. Y equals negative 90x plus my original starting point, which was 1,710. It really doesn't matter which way you write this equation for this problem. And so if I know that, that helps me with my y-intercept, b, and my slope is down 90 and over 1. Again, you'll want to pause your video, but the y-axis is elevation, as you see here, and the x-axis is the number of hours. What I've decided to do is make all of my tick marks, my little tiny tick marks, 90, but I only marked every 4 so it doesn't get crowded. And I made every single one of the tiny tick marks down here 1 hour, but I only marked every 2, so 2, 4, 6, 8, etc. You can't really read those numbers very well. I apologize for that. So then I started up here at 1,710 feet, because up here was 1,800. So I start at the original elevation, and I go down 90 and over 1. Down 90 and over 1. And I continued that pattern throughout. Now the last thing I have to do is think about if I should connect the dots. And does it make sense to have a number where we have a half an hour? So yes, the elevation would be somewhere in between these two dots after a half hour. So I'm going to go ahead and connect the dots. Now by graphing that, it helps me answer this question found over here. How many hours will it take the robot to reach the base of the hill? If I have the graph, I can just look at where the robot gets down to an elevation of 0, which is the base of the hill. And that took, remember, each one of my tick marks is one single hour, so that took 19 hours. So that's an easy way to see how long it takes. With those examples, you should have enough information to be successful on the worksheet for section 7.2 now.